Authored by a veteran chemistry teacher, Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up and don't forget to subscribe. We will see you in the next video and thank you for watching.
Today we'll be talking about soaps and detergents. I'll give you a few examples of soap and detergent molecules. We're looking at hardness of water and the ways of softening hard water, and we'll also look at a few activities that investigate the causes of hard water. Have you ever thought of what the conditions would be like without soap? Developed by the medieval Arabs, it benefited our world in immeasurable ways in terms of health and sanitation. As a cleaning agent, water by itself will only be able to dissolve some substances from materials that have to be cleansed. These include polar compounds such as acids, bases, and salts. Others that do not dissolve in water will be left on the fabric. Washing a dirty t-shirt, for example, with water alone would only remove substances such as urea and the ions that got onto it from our sweat. The fatty sebum and other non-polar, oily, or greasy particles will still remain in the fabric since they are immiscible in water. The use of soap along with water allows for these polar as well as non-polar substances to be washed away from the fabrics. Soap molecules bond with both these non-polar particles on the fabric as well as with water molecules. In this way, water is able to wash away non-polar compounds and other substances that have to be cleansed from the fabric. Nevertheless, the cleansing action of soap can be negatively affected by some dissolved ions in water, such as calcium and magnesium ions. These ions react with soap molecules, precipitating them out of solution to form soap scum. This process not only wastes the soap, but the soap scum formed sticks onto the clothes and also block drainage pipes. Eventual repairs to pipes and the removal of scum from clothes can be very costly. Detergent molecules are not affected by these dissolved ions since they do not form precipitates with them. However, non-biodegradable detergents can cause problems for the environment by accumulating there. This chapter explains how soap and detergent molecules are able to cleanse fabric of both polar and non-polar substances. It also investigates how calcium and magnesium ions affect the action of soaps and detergents and how water is treated to remove these ions. So what we're showing here now with these two molecules on the left and right are the way in which a soap molecule and the detergent molecule are designed. This is here the soap molecule, sodium stearate, and this one here is a detergent molecule. It's called sodium paradicyl benzene sulfonate. So here is a soap molecule and this is your detergent molecule. What is common with both of these is this long hydrocarbon chain here. And of course, you know, hydrocarbons are nonpolar compounds. By virtue of having these long nonpolar tails here, it makes one end of both the detergent and the soap molecules nonpolar. But if you look attentively, you can see the other end here has a small negative charge, and that makes the other end of these molecules here polar. This is a generic model of either one of those. So this long hydrocarbon chain that you have here is hydrophobic, is water repelling, but it can be connected or attracted to grease particles on the fabric that has to be cleansed. Okay, The other end is deliberately made to become polar because you want this end to connect to the water molecules. So via this guy, we can connect a non-polar compound to water molecules that are polar. So that is the specific design of either a soap molecule or a detergent molecule. So let's see how these particles here are arranged in water. If you have these soap or detergent molecules here, you will see that they form this arrangement that we call a missile. What you're seeing here is all the detergent or soap molecules are having their non-polar ends connected to each other or very close to each other because they love each other, non-polar. And because the polar ends are charged, they repel each other like that. But the polar ends are connected to the water molecules by dipole-dipole forces. So this is how these detergent or soap molecules are able to form these spherical, you see this in 2D, but actually they're spherical in nature. Now let's see how a detergent or soap molecule is able to cleanse a fabric of all your greasy particles. So I'm going to leave this here for you to watch. You can read that, and then you can look at the picture there and try to figure out what is going on. I don't want to give you the answer, right? What are you seeing? You're seeing how these molecules here with their non-polar ends got stuck into the grease particle here, okay? And because they attract the grease particle here, they actually will dissolve away a piece of that grease particle here, and you will end up with your diagram on the right there. See? The grease particle gets dissolved by the non-polar ends of these molecules here. As you can see also, the polar ends of the soap or detergent molecules are attracted to water molecules by dipole-dipole forces. These water molecules in turn are attracted to other water molecules by hydrogen bonds. The sodium ions are spectator ions and are not involved. So here's a brief summary of the processes involved in the cleansing of a fabric of grease or oily particles by either soap or detergent molecules. Their non-polar ends or hydrophobic ends dissolve the grease particles by London dispersion forces. Their polar ends or hydrophilic ends are attracted to water molecules by dipole-dipole forces. These molecules are attracted to other water molecules by hydrogen bonds. Like this, water is able to remove these grease or oily particles via the soap or detergent molecules of the clothes or fabric. As the water moves, it takes away these molecules with their connected grease or oil particles. Hard and soft water. Look, this is what is happening. I explained to you already when we did water as a solvent. Groundwater is the water that runs over the ground as a result of melting ice or rain falling. As water runs above the ground, it does not discriminate between what type of substances it dissolves. So water will dissolve everything in its path that's soluble in it. All these different ions here, right? Some of them could even be poisonous and stuff like that. We're saying the presence of these can cause health and environmental problems. One of the problems frequently encountered is in its use in doing laundry using soap. People experience that such type of water requires more soap than usual to do their laundry. The soap does not lather up that easily, so they describe the water as being hard. It is found that it is the presence of calcium and magnesium ions in the water that produce this effect. So let's see what is the definition of hard water. So the causes of hard water, we said already, is due to these ions here, right? In the absence of these ions here, a soap solution will form a lather very easily in water. Such water is described as soft. The amount of lather formed is an indication of the soap's ability to cleanse. If water contains these ions now, right, they react with the soap molecules to form precipitates. The removal of the soap molecules from the solution or water makes it difficult for the solution to lather. Such water is said to be hard. These reactions not only waste the soap, but the precipitates formed are nuisances in many ways. They cling to onto the clothes. You must have noticed that sometimes when you're doing the washing, you see a little whitey precipitate there. That's what is happening because these guys are reacting with soap to form these precipitates. They stick to bathtubs and are responsible for pipe scale deposits. So what happens after a time if you have a laundromat or something like that and the water is passing through a pipe, the deposit of these precipitates foam will eventually plug up the pipes. So if that is the pipe here, eventually it's going to try and get smaller and smaller because of the scale deposit on the inside of the pipe there. So see how precipitates are formed. So the magnesium ions that are present in the water react with the stearate ion there, this is your soap, and it forms magnesium stearate as a precipitate. See the solid there is a scum. Same thing happens with calcium here. When it reacts with the stearate ions there, or the soap molecule, it forms calcium stearate as precipitate, and these will what we call scum. I'm trying to depict to you what is happening here between the soap molecules and the presence of magnesium and calcium ions. Okay? So what we said is this. When you have these ions there, they will quickly react with your soap molecules here and form precipitates. See? Look. You have magnesium holding on to those ions there to form scum, a precipitate of magnesium stearate or calcium stearate there. So effectively what is happening here is you are actually removing these guys here. They're actually removing some of these soap molecules from the solution. So look at the result. You start with all of these soap molecules there, and because of the presence of magnesium and calcium ions, you're not left with less. Okay? So this guy will not lather up very quickly. It wouldn't lather much because many of its molecules have been taken away and deposited as the scum here. Compare that with a water that is soft, that doesn't have any calcium or magnesium inside. See, lots of free soap molecules are there. So that's why they lather up very quickly, and this will be more effective in cleaning than this one here, because this one here will have less soap molecules, and then you have this scum that is formed here, which is a nuisance, gets stuck onto your clothes, goes down the pipe, blocks it up, and form these scales. Water softening. Water softening can be done in two ways. The whole idea is to remove these ions from the water. So people make use of what's called an ion exchanger. Okay? This is how an ion exchanger works. It is filled with what is called a resin. Resin is a giant organic compound, hydrocarbon, that is found in plants. But it was sulfonated by reacting with these sulfur groups here. But before the exchanger is used, they pass concentrated sodium chloride into it. They prepare this ion exchanger by having the sulfonated resins react with sodium chloride. So what happens is that the sodium ions take up this position here on the resin, okay? So what you're having is all these saturated with sodium ions. Now it is ready for use. So what happens is this. The calcium and magnesium ions exchange places with the sodium ions. They see they're trying to exchange places there, okay? The final result is this, look. The final result is this. See, they take the place here. And what comes out here is soft water. the soft water, but it also contains the sodium ions that have been removed. All right, so two things to note here. One, the water that is coming out is soft. Calcium and magnesium ions gets stuck onto that thing there, or they get exchanged for the sodium ions. But the water that is coming out also has sodium ions inside. So people who are very sensitive to sodium ions, such as hypertensive people, will have to be very wary of this fact, because if you're using water that is made soft by an ion exchanger, note that you'll have a higher concentration of sodium ions, so you'll have to know how much salt and stuff like that to put in the food, knowing that you get some from this source here. All right. Finally, now after this thing has been used for some time, you can see all the sodium ions are removed from there, so there's no more sodium there to do the exchanging of your magnesium and calcium. So what you have to do after a time, they'll stop using this and they replace it again with a solution of sodium chloride, all right, concentrated sodium chloride. So the sodium will knock these off, bring them out, and take the place here again, and it will now be ready for use. Okay, so that is how an ion exchanger works. You first of all have a resin inside there. You prepare it by passing sodium chloride here. Sodium ions get stuck onto that there. When you pass your water that's hard, there's exchange between the sodium ions and the calcium and magnesium ions. Eventually it's become saturated with these ions there. It's not functional anymore because there's no sodium there to exchange places with these. So what you have to do there, replace it back with this sodium chloride to push these out and to get fresh amount of sodium there. For that to happen, and what we said, know that sodium is coming out there. People who are having sensitivity to high sodium should be conscious of that. Second method of removing these guys is to let them react with something that will precipitate them. And what we are doing here is reacting it to sodium carbonate solution. That dissociates like this to produce these carbonate ions. And carbonate ions, when they encounter magnesium ions, will form a precipitate of either magnesium carbonate or calcium carbonate, or both of them, if both sets of ions are present inside here. All right? So that is a second method of how you remove magnesium and calcium ions from hard water, or how we soften hard water. So we'll see you again next time.